Hi there, I'm Paul Hazelbeck and I'm going to be talking to you about an apparatus for expanding PTFE, which stands for polytetrafluoroethylene, also known as Teflon. So, PTFE, what is it? It is a type of polymer that can be used for a variety of jobs. W.L. Gore and Associates were the first people to expand PTFE, and Gore uses PTFE for waterproof and windproof fabric, along with vascular grafts. Other famous uses include baghouses, which use PTFE as a filter to filter out particulates, and as a nonstick in cooking for pots and pans. I will be discovering a new process for expanding this material for Company X. On the right, you can see a picture of PTFE tubes, and this is what the company originally used for their process of elongation, but I'll be using solid tubes instead. And the reason for that, as you will see later, is for gripping onto these tubes. There are several different problems Company X has when they try to stretch PTFE. One being that they have a 90% defect rate. This is because the tooling fixture cannot hold on to the part as the temperature is rising. By having only a 10% success rate, the process is wasting 90% of the material and labor going into it and does not meet a cost-effective solution. The inefficiencies are costing the company roughly $500 per sample. Along with that, they aren't able to get as much as they can out of the material by not knowing what parts are successful and why. Another problem, as you will see later, that I found by my literature review is that the material is pulled at a fixed rate. Along with that, the overall testing time is 1 hour per part. I need to expedite the process by figuring out a way to decrease the loading time. The loading time is taking a long time because the heating and cooling of the system is drastically slow. The overall sample time, like I said, is 1 hour per part, and if I were to continue at a rate of 1 successful sample per 10 hours, it would take years to make enough samples to develop a process. Which leads to my first goal of reducing the sample time from 1 hour to 30 minutes. My second goal is to have at least a 50% success rate of samples. And this leads to my third goal, which is to find the optimal temperature, force, and expansion rate from the motor that will make the maximum elongation of the PTFE sample. For my literature review, I looked at several different components. I looked at temperature, tooling fixtures, reloading time, and how to expand the material in a cost-effective way. Some key highlights I took away are the 3 you see listed here. All 3 of these have helped me narrow my scope and have helped a lot in what I should focus on for design, along with how I should design the system in general. The first one comes from W.L. Gore's first patent on PTFE expansion, and he states, "The porous microstructure of the expanded material is affected by the temperature and the rate at which it is expanded." The second one is that costs, size, material availability, dimensional stability, durability, and the maximum processing temperature are all important for designing tooling fixtures. This helped me figure out what I should focus on for designing my tooling fixture and how I should design the tooling fixture itself. The third point is that temperatures to initially operate at in the testing apparatus might ideally range from 327 to 450 degrees Celsius. This is a good starting point where I will initially start my tests as I seek to find the optimal temperature for elongation. For my design and improvement strategy, I decided that it would be best to construct the testing apparatus as an insulated chamber to maintain high heat throughout the entire process. To do this, I will design a 2-cylinder chamber, one that has an inner overlapping chamber to keep as much heat as we can inside the system, and the outer chamber to protect me or whoever's operating it, since we are operating at such high temperatures. My second improvement strategy is to CNC machine 2 identical sets of tooling fixtures to switch out and reduce cycle time. Like I said earlier, one of the most important things is the cycle time for figuring out what process will be best. And what I've found is since we are operating at such a high heat, that cooling time is a major factor. My third point is to make a tooling fixture with teeth that can hold onto the part or clamping down in a way that changes the inner diameter so the tooling fixture will not slip off the end. This is because the tooling fixture cannot hold on to the part at such high heat. And my fourth is control over the speed of the motor to control the rate of expansion by installing a VFD, which stands for variable frequency drive, because as we've seen in other past successes, temperature and speed of the motor is highly important. To measure success in Company X's apparatus for expanding PTFE, I'll be using dial calipers to see if the diameter stayed consistent as the PTFE is stretched. I also make sure the grip strength of the tooling fixture will withstand the whole operation. The PTFE also must be stretched to a certain amount. And finally, the temperature, expansion rate, and force/tensile strength will also be taken and analyzed in Minitab to understand how to maximize the elongation process. This will be using IME 327 techniques, along with my knowledge from past IME classes, to change and optimize this process. Thank you so much for your time, and I hope you've learned a lot about expanding PTFE, and I can't wait to share my progress with you on this exciting senior project.